Hello everyone, my name is Aaron Standard, and today we're going to be diving into part 2 of our How We Built the Fastest MQTT Client in .NET. So if you haven't seen part 1, you can check that out here. We also have parts 3 and 4 planned as well. And today what we're going to focus in on is the packet parsing layer. How do we actually parse the MQTT protocol packets at such high speed, and how do we actually also encode them at high speed as well? We're going to be using System.Memory to do all this today. So if you're a .NET developer and you're interested in learning about how to do really high performance, like bitwise code where you're doing bit banging, or maybe you have to serialize things, this will be a good instructive video that kind of shows you some of the things you need to do in order to make sure you get good end-to-end performance all the way around inside your application. So let's dive in and start taking a look at some of the details. The business problem that we had to solve with TurboMqtt is that all MQTT connections are typically just a single TCP connection. This is true for whether or not you're a device out in the middle of a field somewhere transmitting signal data to an MQTT broker, or if you're a business application consuming that data in order to do something. Typically, each MQTT client, whether you're a publisher, a subscriber, or both in some cases, each client will typically use a single TCP connection for handling all these different subscriptions back and forth between the broker. This means that MQTT is susceptible to a flow control problem that we just made a video about called head-of-line blocking. This essentially means that packets that are going through the pipeline can block other packets behind it. Therefore, the amount of time it takes for each one of these MQTT packets to get processed is going to be dependent on all the different things sitting in front of it inside the TCP stream. So in order to make this system as responsive and as fast as possible, we have to guarantee that that packet processing time is as short as possible. We can't do a lot at this stage of our code to go ahead and manage how quickly the I/O system is able to buffer packets back and forth. That's something that we'll address in some of the later parts. But here we're just focusing on trying to make sure that once we get the data out of the processing pipeline, we have to try to parse those bytes that we're receiving into the formats that the MQTT subscriber or publisher can understand. We need to be able to do that as quickly as possible. So that's what we're going to be focusing on today. Now, this is what the MQTT packet structure looks like from a binary point of view. Every single MQTT packet must have at least 2 bytes. 1 byte is your control packet, which basically describes the type of message that we're sending. So the MQTT protocol only describes a handful of different packet types. We're going to take a look at those in a moment. And there's some flags that each of these packet types might include, such as, should you retain this message? Is this message a duplicate? What quality of service are we using? Etc. Next, you have at least 1 byte that describes the remaining length of the rest of this message. Some packets might only be 2 bytes long, just the control field and the remaining length. But other packets might be significantly longer, including the most frequently used packet, the publish packet. The publish packet is where all the actual data that our devices are emitting and consuming comes from. So those packets can be quite large depending on the size of the payload that we're sending. So we might have up to a 5 byte length header. We might also have some additional headers. So for instance, MQTT5 supports things like tracing. I could go ahead and put a tracing header inside that little variable header field right there. And then you have your payload, which might also have some additional schema and data structure to it as well. So we need to be able to support all the different packets and all the different binary structures, which all generally follow this specification. From a C# perspective, we have kind of an abstract way of reasoning about it inside TurboMqtt. First, we have this abstract class, our MQTT packet type. So this is going to have a little enum that describes which packet it is. And then we have some of the other control headers that are very common inside these packets, such as duplicate, retain, quality of service, etc. Not every packet supports all of these, but some of them might. So we just go ahead and include them, and we set hard-coded values on them by default. If a packet does need to set this value, they can go ahead and override that in their implementation. And then finally, the most important packets in the system typically come with a sequence number, otherwise known as a packet ID inside MQTT. We made a video about this, about making illegal states unrepresentable. That non-zero unsigned integer is 16. It's basically an unsigned short that can't be zero. That is how we identify packets uniquely inside MQTT. We made a video about that here. But this is what our C# packet structure looks like. So we need to be able to go from that binary structure we just saw to this structure and the other way around. So from a packet grammar standpoint, we have to support, it looks like maybe about, I don't know, a dozen different packet types here. So we have a couple of packets that deal with heartbeats. We've got 4 that deal with connectivity, 4 that deal with subscriptions, and then 4 that deal with publishing. We need to be able to handle this not just for one version of the MQTT protocol, but for 2. There's 2 major versions of MQTT that are kind of widely used. There's the 3.1.1 version of the protocol, and then there's the newer version, the MQTT5 protocol. MQTT5 packets tend to be quite a bit bigger, potentially, than the MQTT 3.1.1 packets, and this is because they support all these additional headers and also controls for doing things like token refresh and authentication and that type of stuff. So there's more things we have to do. Ultimately, TurboMqtt has to be able to support both. At the time of writing this, everything we've built has been mostly around the older MQTT protocol implementation 3.1.1, but we will support both in the near future. Now, what performance concerns do we have when it comes to working with MQTT packets? Well, on the outbound side, where we're writing packets to an MQTT broker, we care about encoding. This means that we need to worry about reusing buffers and allocating memory. One of the number one things we could do to kill the performance of a TurboMqtt application is creating a lot of garbage collection pressure, especially in the form of lots of small, relatively short-lived byte arrays. So we want to try to reuse buffers as best as we can. That'll allow us to go ahead and potentially alleviate that source of computational overhead from our applications. And then finally, there's the raw packet serialization and encoding. We have to take all of this data, which could be in string, integer, or potentially binary format, and we have to represent everything as bytes and then transmit them over the wire and encode them accordingly. Finally, we also have to worry about packet decoding, and this is usually where the packet encoding, it's a little bit easier to kind of navigate because you're starting with your strongly typed representation of data and translating it to binary. Packet decoding is typically, in most of my experience, a little bit more expensive to do because you have to figure out how to go from an array of bytes to having, let's say, a C# or an F# object again. And that can be a little bit more difficult. In our system, since we have a relatively limited number of grammars we have to support, we don't have to do crazy things like support arbitrary deserialization, which is something we do have to do over on the akka.net project. But the problems we still have to deal with here when it comes to packet decoding, a classic problem you're going to run into with both TCP and UDP is having to do partial message handling. This is where you only receive a fragment of a message. Therefore, you're not able to fully parse it until you get more data from the network. And then we also have to worry about just generally our packet parsing speed. How can we make sure that we make our way through these byte arrays, which might contain multiple packets? How can we make sure we do that as performantly as possible? So our plan, and we're going to show a whole bunch of code supporting this, our plan is to leverage System.Memory, which is a new set of APIs that were first introduced into .NET. I say new, but they're actually probably 5 or 6 years old now. I think this was all introduced in .NET Core, either 2.0 or 2.1, maybe it was .NET 3. But this is basically a set of APIs that are designed to facilitate zero copy manipulation of byte arrays. So being able to go ahead and traverse up and down contiguous segments of memory without having to copy. That's really nice. It also has a bunch of really important buffer pooling capabilities as well. And there's a lot of support in some of the higher level APIs we're going to use, such as the UTF-8 string APIs, that all can leverage this to do zero copy operations in that universe accordingly. So this is a really useful set of tools for us to work with in order to try to achieve our goal with as little duplicate memory usage as possible and with the highest performing parse speeds as possible as well too. So some of the things we're going to do here is we're going to leverage the IMemoryOwner construct for buffer pooling. This is how we can basically rent buffers and then return them when we're done using them. This will get used really heavily, particularly on the right side of our application. But one of the techniques you have to implement in order for IMemoryOwner, or really any type of memory pooling, to be effective whatsoever is you have to have a really good technique for being able to estimate how much memory you really need. Now, if you're just doing things like using a fixed size buffer and paging content out of a file, then this can be really simple. You can just use a constant for that. But if you're doing things like taking variable size packets and encoding them onto the wire, you have to be a little bit more sophisticated than that, which we have to do here. So that's one thing we're going to take a look at. The other is we're going to design, since we're working primarily with value types, so these are structs, not classes usually, we're going to have to design most of our methods to use reference parameters and inlining aggressively. That way we're not accidentally copying some of our value objects as they're being passed through multiple functions. So this is something that's like kind of a mechanical sympathy technique designed to basically make sure that we can kind of navigate through the stack without having to copy data around. That's really the goal behind this. Now on the read side, where we're processing incoming packets, we're going to use the technique known as bit banging. This is basically where we're going to kind of emulate signal processing in software, more or less. But what this means in practical terms is we're going to consume the byte stream sequentially. One of the things that's kind of interesting about the incoming messages is that we're going to receive an array of bytes, and there might be several messages in it. So we need to sequentially parse these because TCP preserves order, and also the MQTT protocol wants us to preserve order as well. We're going to sequentially parse this stream for incoming messages and then emit those deserialized messages in the order in which we extracted them down to the consumer. So this is our plan. Let's go ahead and start by taking a look at some benchmarks to kind of get a sense for how quickly is the system that we built able to actually work. Let's take a look at that first. All right, so I have some of our benchmarking figures here. Now, I actually went ahead and I ran our full suite of benchmarks, but we don't explicitly measure the total amount of encoding and decoding time it takes for every packet type because there's really only one that is significant, and that's the publish packet. That's where all of the useful data you actually care about is going to either be sent to or received from an MQTT broker. So that's the primary packet that we are going to be dealing with today, is the publish packet. So here we have, this is a parameterized benchmark.NET benchmark. We have various packet sizes that we're going to encode and decode. 1 kilobit, 2 kilobits, or kilobytes, 4K, 8K. And one of the things you'll notice here is that some of the times jump around a little bit. We have encode and decode, so we basically measure both of these. But you'll notice that in some cases, we have, let's say, the first benchmark that we ran, decoding a 1 kilobit package, we're doing about 275,000 messages a second. Whereas when we're decoding a 4 kilobyte package, we're doing close to 700,000 right there. So what this kind of tells you is that the rate of basically processing this benchmark can achieve is somewhat dependent upon the load that's on the machine. Unfortunately, the machine that we use to benchmark this, it's the newest and most powerful CPU that we have in the office, but it's also running a Kubernetes cluster and some other workloads that are on it. So that's probably why the numbers jump around a bit. But this kind of gives you an idea. If we take the largest number from here, this is basically what your peak performance can be. And this is pretty consistent with what we've measured on other computers too, that we can probably decode about, let's say, 700,000 packets or so per second on a really high-end computer. So if you are connected, to a MQTT broker using, let's say, a server that's running in your private cloud, you can probably expect to get about this performance, about 700,000 messages per second. And if we multiply this value, let me go ahead and pull my calculator up. Let's go ahead and multiply 690,882. Let's multiply that by the 8 kilo. Let's see, this is 4 kilobytes, 4096. This gives us a theoretical bit rate of about 2.8 gigabytes per second of data coming over the wire. You're not going to get that type of throughput from an MQTT broker because this is actually, surpassing NIC speeds in some environments. Even if you had a 10 gigabit NIC, it's very unlikely to have a broker that can actually distribute data this quickly. So this means that we can safely rule out the MQTT, decoding pipeline as a source of bottlenecks inside the system. That's the entire goal. The I/O system, the thing that's actually responsible for receiving and sending these bytes over the network, is probably going to be the bottleneck instead. That's good. That means that basically we haven't done anything inefficient in our application that would cause us to run slower than the underlying network infrastructure can. That's the entire goal. So I wanted to kind of start backwards and to show that, look, the end result that I'm going to show you here actually achieves its goal of making sure that our encoding and decoding pipelines aren't the source of the performance constraint inside the system. That is going to be the network is more than likely going to be where it belongs. The other thing I wanted to show before we dive into the code is that generally, yes, the encoding pipeline is going to be significantly faster than the decoding pipeline. So the max performance we got here was we're able to encode about 2 million messages a second or so. And that makes a lot of sense. And the reason why is that when you're encoding packets, you know how big they are from the offset because you have all the data there. And that's a much cheaper operation versus when you're decoding packets, you may not necessarily know until you've made it a fairly long distance through the byte array, basically how much data you're dealing with and what all is there. So those various things we could probably do to speed this up even more with TurboMqtt. But as far as I'm concerned, we hit our performance goal, and the real, let's say, bottleneck inside the system is more than likely going to be the asynchronous I/O we use for paging over the network, which is something that we're going to address in a later video. So without any further ado, let's go ahead and take a look at some of the code that we use to actually achieve these speeds. So the first thing we're going to take a look at here is some more benchmarks, actually. We're going to look at our packet size estimator, which is the first component we need to make the outbound side of our transmission system fast. And as you can see here, we've measured how quickly we can estimate the size of a packet for every packet type that we support. This is just for the MQTT 3.1.1 version of things. And some of these packets we can estimate at a rate of like 1.2 billion per second. And then our slowest packet, which is the connect packet right here, we can do 41 million of those per second. And then for our publish packet, which is right here, we're doing 178 million of those per second. So the whole point of this is that the packet size estimation is actually fairly inexpensive, even for our most complicated packet type, which is our connect packet. It's the most complicated because it has the greatest number of like variable things you have to support. The publish packet is the biggest in terms of the total amount of data that it can include, but it's laid out in actually a fairly straightforward way. The connect packet's a little bit more complicated by contrast. So we'll take a look at these. The first thing we should take a look at before we dive into that, though, is our encoding flow. This is the akka.streams workflow, which you can learn more about akka.streams here. Now, we're going to get into a little bit more details about how akka.streams greatly speeds up the overall design of TurboMqtt. I think we're covering that in the next video. But let me just kind of quickly walk you through our encoding pipeline. The first thing we do is we accept an MQTT packet. That's the abstract class we looked at earlier. And we create a tuple that has that packet and our estimated packet size right here. That's going to be the first thing we look at. We then have a filter that drops packets that are bigger than the maximum frame size that we can support. This is usually a constraint imposed by the MQTT broker, and these messages will get dropped anyway. We're just kind of not even bothering transmitting them on the client so we don't waste bandwidth or potentially get disconnected from the broker that way. It's better that we handle it than wait for the broker to do it. So that's why this exists. And then we have batch weighted. This is some akka.streams magic for being able to take multiple frames and encode them together. That way we're using fewer trips to the socket to transmit the same number of bytes. This will help greatly improve throughput overall. We'll cover that in some more detail in the next video. And then finally, we have the MQTT encoder. This is what actually takes these MQTT packets and turns them into bytes. So let's start by taking a look at the packet size estimator and learn a little bit more about how that works. All right, so the packet size estimator works by basically just using a switch statement, and based off of this little enum we've described, we have different methods for trying to estimate how big these packets are. So let's take a look real quickly at, let's say, these ones down here: ping request, ping response, and disconnect. These are the simplest possible packets in our system because they only require the 2-byte header. So we basically have a constant that we return back for that, fixed header only. So that's pretty simple. But for something like the connection ACK packet, we actually have to return a 2-byte payload in addition to the 2-byte header. So one for the session present byte, which has some flags, and then another byte that has the reason code for specifying why we acknowledge the connection or why we didn't acknowledge it. There can be various conditions there, such as an authentication failure. The packet size struct here, this is kind of following that video I linked to earlier where we talked about make legal states unrepresentable. We basically break down the size of the packet into its various components. First is the payload size, which is basically going to be the determinant of how big the other headers are. So we go and estimate how big the variable length header is going to be based off of the content size here. And then we have the total size, which we do by adding these three values up. Now, in theory, we could probably cache these values and that would speed things up a little bit, but not by that much. Plus, things like dynamic profile guided optimization will probably inline some of this anyway. So I'm not super worried about that, but we could, in theory, make this a little bit faster by doing some of those things. The thing we really want to take a look at is how do we actually go about estimating the size of some of these packets? Well, let's take a look at the connect packet, which is the most complicated. So here in my comment, I've kind of laid out basically the structure of this packet according to the MQTT 3.1.1 specification. MQTT 5 is actually more complicated because they have basically a richer authentication modes. They also have support for things like tracing in some of these packet headers. So we will have to account for that in our MQTT 5 implementation one day. But for 3.1.1, we include all the really important stuff. So the first is the protocol name. For that, we have to include basically 2 bytes that describes the length of the string plus the string itself. That's what this is right here. So we're going to go ahead and encode that. Next, we have to encode the protocol version. So this is specifying what version of MQTT that we're using. Then we have some connection flags. We need a single byte to encode those. Then we have our keep alive value. We need 2 bytes to go ahead and encode that. And then if we have a last will and testament, which is basically a way of essentially telling the broker to send us a custom payload back in the event that we get disconnected. We have to go and encode that as well. There could be some more data involved with doing that. And then finally, if we have authentication, we might have the username plus the password. We use 2 bytes basically for each of these string fields to indicate how big that next piece of data is going to be inside the system. Now, all of these values are all specified in the MQTT protocol, so I don't have to guess any of this. This is all part of the specification that's built in here. And actually, as it looks like, I actually do have the MQTT 5 implementation finished. We haven't actually added encoding support for this into our application yet, but it's all here. So the basic idea behind this is we want to accurately compute how big the packet is, how big the variable length header is, and how big the total length is before we feed that packet into our actual encoder. The encoder is the thing that's going to actually write this into a contiguous byte array by the time we flush everything out to the network. So let's take a look at our encoder flow. Our encoder flow gets access to a memory pool. So a memory pool is a construct introduced in System.Memory for being able to do buffer pooling. So I think by default, if I take a look at where we encapsulate this here, memory pool, there we go, memory pool byte shared. So we're basically using kind of one of the static shared pools that's shared throughout this process here. You could create a custom memory pool if you wanted to, where you have one pool of bytes that's being shared by this client, another pool of bytes being shared by that one. There might be various advantages to doing that. We're just using the global static shared memory pool here, and that's good enough for our purposes as far as we're concerned. We're going to use that shared memory pool, and we are going to, as you can see here via the packet shape, we're going to accept a list of MQTT packets with their predicted size. So that's going to be our input that we accept in the encoding pipeline. And the output is going to be an IMemoryOwner. That's going to basically be a shared buffer of bytes. And we're also going to include a little hint as to how many bytes in that buffer are readable. The reason why we're going to do that is that when we work with the shared memory pool and we request a memory buffer, we may not get exactly the same number of bytes that we're requesting. We might get slightly more than that. And that's because the buffer pool is going to try to reuse things that are going to basically potentially contain enough data in it to work for multiple use cases. So if I request 12 bytes, I might get a 128 byte structure back, which means that not all of it is readable. That's why we include this value here. The akka.streams bit isn't super important, but this is where the interesting part comes in. Basically, we're going to go ahead and grab that array of basically packets and their estimated sizes. We're going to go ahead and grab that array from the akka.streams code sitting above us. We're going to compute the total predicted size from all those packets here. So we're going to go ahead and sum the size of the payloads and their headers. And we're going to tell the memory pool that we want to rent a buffer of this size. This is where the IMemoryOwner comes into play right here. So the IMemoryOwner is our basically way of saying we're going to temporarily own this memory, and we're going to return that memory when we're done using it back to the pool. This is so we can avoid having to allocate new buffers all the time. And this will help keep our garbage collection pressure a lot lower inside the system. So we go ahead and we rent that memory, and then we're going to extract the memory struct from that memory owner. It's just a property. And we're going to feed that writable buffer and all of the packets that were included in the akka.streams input here. And we're going to feed it into our static method here, MQTT311 encoder.encode packets. And this is where the magic begins. For each of these packets, we are going to basically grab the packet and its size, and we're going to feed it into this encode packet method. We're going to go ahead and pass the packet in. The packet's a class. The buffer is a value type, so we're going to go ahead and use a reference to basically make sure we're referring to the exact same buffer. And then we're going to pass in our packet size data structure. Actually, I guess I'll go back to the top up here. After we encode each packet, we're going to get a value of how many bytes were written. We're going to slide the buffer forward. This is a little bit of bit banging on the right side. We're going to slide the buffer forward and say, okay, this working buffer is now equal to this value. So the new starting position of the buffer is going to be the end of where we just wrote. So if I have let's say a buffer that has 100 bytes in it and I just wrote 10, if I call slice 10 right here, this is going to reset the buffer to the 10th packet. So packets 0 through 9 contain my previous message. Packet 10 is a zeroed out byte that hasn't been written to yet. We're going to go ahead and write that with the next packet we're going to go ahead and encode. That's how this works. So we're going to go ahead and basically slide the buffer forward. So we're going to go ahead and call encode packet down here. And let's take a look at our publish packet. So that's probably the biggest one we have to worry about. For this publish packet, what we're going to do is we're going to take this memory and the estimated packet size. And the first thing we have to do is we have to write the first byte of the fixed packet header. So that's that header that has all the control values, such as what's my packet type? Is this a duplicated packet? Is it retained? We have to always write that first. So we have a little method here that's going to take a look at the packet type, the quality of service, retain, and we're going to go ahead and use a little bit of binary arithmetic to set these values. Now, I'm not going to go ahead and explain how to do all of that in this video. That's an exercise better left to the reader, and that could be several videos on its own. But this is a technique that's available in every programming language. This is just us essentially setting individual bits on this byte is what we're doing. So we're actually doing bitwise encoding rather than byte-wise encoding here. So we encode that first byte and we write it in the first position. And this is how bit banging works. We're going to go ahead and assign the front of this buffer. We're using a span now rather than memory, by the way. So we're going to pass in the span, which is a ref struct. We're going to assign the first byte equal to this byte value that we calculated. And then we're going to go ahead and just move the buffer forward. We're going to go ahead and slice the buffer one at a time. So the reason why we want to do this is that this span kind of allows us to work in a local context for this specific packet that's being written into a buffer that multiple packets might be a part of. So we're mutating just this packet's individual buffer, not the memory, which contains the buffer that all the packets sit inside of. So it's a segregation of duties is what we're performing here. And that's important for making sure we stay on top of everything. Next, we're going to go ahead and encode the variable length header, which we compute from the content size right here. And all that we're basically doing is we're calling encode frame header, where based off the frame header size, I'm going to go ahead and basically set these various bits here. There might be a more efficient way of doing this. Again, the math isn't super important, but I have to potentially encode the header as either being 1 byte, 2 bytes, 3 bytes, or 4 bytes, depending on how big the content length is. That's what this value figures out, is how many bits do I actually need to set. And it'll set as many as are needed. And then once we are done with that encoding process, we go ahead and we slide the span forward again. Again, this is bit banging on the right side. Next, we encode a UTF-8 string, where down here, I'm once again using spans. I can go ahead and get the byte count using my UTF-8 encoding. So we know that's how big the string is. We're going to encode an unsigned short integer. That's our 2-byte representation for the length of this field. So this is going to say how long the string is. So we're going to encode that right here. So we're going to encode these two values, and then we're going to slide forward. And then we're going to actually go ahead and grab the bytes from the string. And we are going to compute basically we're going to go ahead and slide forward once again. And we're going to go ahead and return basically our unsigned short value, which is 2, plus the string length. And then as I keep going here, now that we've gone and we've written basically the header, the variable length header, we've written the topic, the next thing that we need to write is that in the event that we require a sequence number, we have to go ahead and write that on the packet. So at that point, we're done with all the headers. Now we have to go and write the payload, which we can do via a really simple copy operation. The packet's payload is just a read-only memory structure. We can go ahead and turn that into a span, copy it into the remaining data, and then return the value. So this is essentially bit banging on the right side is what we're doing. And we're just going to repeat this for every single packet that's in the buffer until we return, if I go back to our caller right here, until we return basically the total value of all the packets that we've written, and we will push that memory owner out to our underlying IO transport along with a number of bytes that are written. Now, if we want to take a look at what we do just to kind of close the loop on the IMemoryOwner side of things, if we want to take a look at how that works, we can take a look at one of our transports. Maybe I'll look at our in-memory transport here. We also have a TCP one as well. Yeah, here we go. This is basically where we're reading those same values. This is from a System.Threading channel that we are hooking the akka.stream up to. We're going to go ahead and read out this message, which contains the buffer and the readable bytes. And once we know that we're in a position to be able to read it, we're going to go ahead and grab this buffer. And we're going to slice it. We're going to start at 0. And we're going to grab it all the way up to its readable byte length. And then we're going to go ahead and push this back into, because this is an in-memory transport, we're actually echoing these messages back to ourselves, what we call handle bytes right here. If this was our socket-based transport, we would go ahead and be flushing this to the socket. Once we're done doing our work, whether or not it succeeded, we go ahead and we call dispose on the IMemoryOwner right here, this little message buffer. This is going to allow us to basically return this buffer that we are no longer using back to the pool so it can get used again. This is how we avoid that garbage collection pressure and how we keep the memory growth under control. We always have to remember to return the IMemoryOwner back to the pool from whence it came. And we just do that by calling dispose on it. So that's the right side of how we've attained some of this performance right here. Basically just kind of computing the size of the packet that we need and then laying out all the content sequentially in it. If you're trying to do this using something like a reflection-based serializer, it is not going to work very well. You need to have a way of being able to pre-compute how much memory you need on the right side in order to use buffer pooling effectively. That is what makes this whole system work. So the first thing I wrote when we started actually implementing TurboMqtt was my packet size estimator. Everything else got a lot easier to do once we had accomplished that. So the next thing we're going to take a look at is the decoding pipeline. How do we read the packets coming back? All right, so now we're going to take a look at the read side of TurboMqtt's packet processing system. So basically, we have kind of a mirror image here of what our right side looks like. We accept a tuple of IMemoryOwner plus readable bytes as input, and then as output, we emit an immutable list of MQTT packets. This is because one byte array might actually contain several packets inside of it. So we're going to go ahead and try to decode all of them and emit all of them downstream in bulk. That's going to be the most efficient way from a concurrency perspective to try to manage this. So we're going to pass all this into our little decoder flow down here. And the real code is in the onPush method. This is what basically gets invoked when the transport sends us data. So the first thing we're going to do, grab our memory owner and our readable bytes, and we're going to create a memory structure right here of just the readable bytes. Because, once again, if we're working with memory pooling, we might actually have more bytes that we can work with in this case here. So we want to make sure we're only focused on using the bytes that are actually readable. That's what this does. Now we have a little optimization right here, and this is actually a subtle but really important point. Memory pooling is not always safe. And it's not safe when you don't know when the memory is going to get released down the line. Memory pooling is one of those things you have to be a little careful about, because unless you are very sure about where the life cycle of that memory ends, you can end up leaking memory like crazy, because essentially you're going to have to end up making the user responsible for deciding when they're going to return that memory to the pool. And that's basically like shipping C++ middleware at that point, or, basically kind of forcing them to kind of manually manage memory. In my opinion, you're better off just delegating that to the garbage collector, which can do a better job of it than you probably can. Because with TurboMqtt, when we ship a publish packet, if I pull up the publish packet structure real quick, if I scroll down here, we have our topic name, and then we have our payload and our correlation data right here. I have no idea what the user's done with all this data. They might retain it for some time and then process it in batch later, depending on how their application's built. Well, if I'm reading a ton of packets all coming out of the shared memory pool and the user forgets to dispose them, I'm going to end up basically leaking memory, and it's going to create a problem for the application. So what I prefer to do is this little optimization right here, where my transport might use what's called an unshared memory owner. This is basically a facade where this memory owner is not really a memory owner. It's basically just a wrapper around a byte array, in which case I don't need to worry about doing this sort of safe copying operation right here. I could just use that memory directly because I know that it's not shared. If this memory is shared, I typically will copy it into a safe collection because of that issue I just mentioned earlier. We don't have a boundary around when the user is done with that data. With HTTP, you do have a boundary around when that user is done with the data, and that's when they finish sending the response back to the caller who made the request. Once you're done with that response, you can free up any memory and any other resources you might have used. That's an advantage that a framework like ASP.NET Core has. Frameworks a little bit more open-ended, like akka.NET and TurboMqtt, do not have that going for them. Therefore, they probably need to trade a little bit of efficiency away in exchange for safety. That's what we're doing here. So this is some of the code we use for basically copying over the readable bytes, and that way we can dispose the shared memory. And then the real decoding begins, where we pass in our memory, and we're going to try to return an array of packets back out. So we accept the read-only memory as an input, and we're going to return the packets as an output. And in the event that there's something wrong with our packet decoding, we can go ahead and return a Boolean right here if we need to. So again, we're going to go ahead and do a little bit of bit banging right here. Now, this is another subtle detail that is important to reason about, which is that when working with data that is transmitted in streams over the network, it is possible to receive what we call a partial frame. Now with TCP, this is fairly straightforward. The reason being is that all packets are transmitted in the original order in which they were sent, and they're received in that order as well. And then on top of that, we basically guarantee reliable delivery. You're not going to end up commingling packets with TCP. The protocol at like the very lowest level of the network is designed not to allow that. The implication here still is, though, that because we're working with arrays of bytes, we're not working with messages, it's possible to only receive a fragment of a message. When that happens, we have to store that fragment inside, we call this the remainder right here. We have to store that fragment inside the remainder, and then we have to use that remainder at the beginning of our next parse operation. So our decoder actually has to be stateful under the circumstances here. That's kind of the safe way of doing this. Now, there's probably a way we could do this to remove allocations, where I could probably just like do a virtual read on the data if I wanted to. But because the memory and span data structures require that memory be contiguous, that's going to be the reason why we're going to go ahead and copy this data into this new byte array. We're basically reconstructing everything to be contiguous. We could probably restructure this, and this would make the system go a lot faster in the event that we have partial frames. So that's what this is all about. Now, the next thing we need to do is, as we start decoding, we need to check to see is our working buffer at least 2 packets long. If our working buffer is not, 2 bytes long, is our working buffer at least 2 bytes long? If it's not at least that long, then we don't have enough data to process any of the messages according to the MQTT protocol. Therefore, we can just return false and bail. If we know the working buffer is longer than this, we can start bit banging. So we're going to start by setting some variables for our packet type, packet size, header length, etc. We're going to go ahead and grab the current span from our working buffer, and we're going to do a little bit of bit banging. The first thing we're going to do is we're going to extract the packet type using a little bit of bit shifting right here. And then based off that packet type, we're going to go ahead and slide the span we're working with 1 byte forward. Then we're going to go ahead and try to get the packet length again. And we're going to basically use this to figure out we're going to go ahead and try to get the variable length of the packet next. So we're going to pass in the current packet, the span, and we're going to get the packet size back out. And you can see here we kind of have to loop through because we don't know necessarily the length of the packet yet. We're in the process of finding it, but we know that this size can be between 1 and 4 bytes in length, and we're going to do that until we basically reach the end of the line here. So we're going to go ahead and figure that out. I'm not going to explain all the details how that algorithm works, but it does work. And then we're going to check to see, okay, I have now parsed my packet control header. I have now parsed my length. Do we actually have enough data to continue parsing this packet? If we don't, I'm going to go ahead and return our read value, and we're going to go ahead and save the working buffer right here. This is that memory from before. So even though we've manipulated the span, we haven't manipulated the memory. So therefore, it's safe for us just to stick this into our remainder field. Now, if we pass this check, it means we have enough data to decode the current packet that we're looking at. We're not concerned with what's in the rest of the byte array yet. We're only concerned with the current packet. We're going to go ahead and check to see what the header length is supposed to be. So it's going to be the size of the fixed header plus the length header size. We're going to use this to adjust the working buffer. We're going to go ahead and slice this down. And now we're left with only the variable headers plus the payload. And then based off the packet type, we have a bunch of different decoding functions that are all specific to that we can dive into. So let's take a look at the decoding function for publish, since this is our kind of hot path for this application. After we get our publish packet, the first thing we're going to take a look at is our quality of service. So we're going to go ahead and grab that. We're going to grab our duplicate and our retained values from this from this control packet bit as well. We're going to grab those. And then the next thing that we're going to do is we are going to go ahead and grab, let's see, the rest of the buffer, advance past the fixed size and header. We're going to decode the topic name. We're not doing, as you see here in my little to-do comment, there's some restrictions on what's a valid topic name and what's not. We assume that the broker would have enforced those, so we're not going to worry about it here. We're going to new up our packet. And then based off the quality of service, if we know that we're at greater than at most once quality of service, there's a packet ID associated with this, so we're going to decode that. And then if the remaining length is greater than 0, it's possible to publish a publish packet with no payload. I don't know why you do that, but the protocol does allow it. We're going to go ahead and basically just set the packet's payload to the remainder of this buffer. And then we're just going to decrement the remaining length. Again, we're kind of doing what we did on the encoding pipeline. We're just kind of sliding the packet down is all that we're doing here. And then we're going to go and return this packet. So let's take a look where we do this. So we return this packet, and we're going to add it to our immutable list right here. One of the things we could potentially do if we wanted to improve performance is I could do an immutable list builder. Maybe that would be a better way of doing this. That way we're not newing up immutable lists every time we find a packet. Maybe I'll go ahead and work on that after this video. But as you can see, we have a switch statement for each of these different packet structures because each one has its own unique schema. Do not try and come up with a cute, generic way of doing some of this stuff. You're not going to get better performance, and you're probably going to get worse results. You're better off just dealing with the actual specification and publishing each packet type individually. There's not that many of them. This took me maybe a couple of days to do. It's not rocket science. You can just work the problem and write the code. So I recommend doing that definitely over trying to do something like coming up with some cute reflection-based framework for doing it. You're going to end in tears if you go down that road. Just parse the packets. So we go through and we finish parsing the packets. After we get down here, now we go ahead and we advance the overall working buffer. So we're going to go ahead and basically slice the buffer from header length plus packet size and advance it forward. Now you may have noticed that we have this buffer for message property right here. This buffer for message property, we're starting from 0 and we are slicing the header length plus the total packet size. This read-only memory that we're passing into these functions is memory that only contains the content of this packet. So all the bit banging we're doing in these methods isn't affecting the actual working buffer we have right here. That only happens at the very end. The reason why we do it this way, where we kind of separate the chopping up of the individual packet from the working buffer, is that this makes it easy for me to reason about as a programmer. This is for my convenience, not for the benefit of the computer. And so I can basically have some visibility to like, what are we actually doing here? That's what this is all about down at the very bottom. So we're going to go ahead and basically ignore all the details for how individual packets are parsed from the scope of this code. That's a problem for the buffer for message value and for these function calls here. I'm only concerned with moving the entire working buffer because whatever's left in this buffer at the very end is going to become the remainder I need for parsing the next packet. So that is the basics of how we achieved this performance inside TurboMqtt using System.Memory and sort of a efficient scheme for bit banging back and forth inside our encoding and decoding pipelines. I hope you found this really helpful. So thank you very much for watching. I hope you appreciated it. And stay tuned for part 3 of this TurboMqtt series, which is all going to be about how we use akka.streams for throughput and latency optimization. So don't forget to like and subscribe, and we'll catch you next time. Thank you very much.